Looking here, radioactive sample has an initial mass of 1,000 grams. After 120 days, only 125 grams remain. What is the half-life of the substance? Okay. Now, we said we start with 1,000 grams. How much time has gone by? 120 days, okay. What's our final amount? 125 grams, good. And then what is the half-life of the substance? That's your X. Remember, half-life, that's the time it takes to cut something in half, okay? So then try and just sort of visualize what's happening in this problem. You have a 1,000 gram sample. Every such and such amount of days, it'll be cut in half. We have 1,000 days, or we have 120 days to do this cutting in half process to get us to 125 grams. So what we want to figure out is, well, how many times, how many half-lives am I doing? How many times am I going to divide 1,000 by 2 to get to 125? Somebody had said 3, I think. Now, that's great if you can do that in your head or you did in your calculator. Let's just, if you're confused, let me walk through it real quick. If I do 1 half-life divided by 2 one time, I'm at 500. If we do a second half-life, I get to 250 grams. I do a third half-life, I get to 125. Okay? So I've done 3 half-lives. So now that's not my answer. The number of half-lives is 3. Okay? So what we got to figure out is what's the length for 1 half-life. Yes, it'll be 120 divided by 3. You're going to want to use this formula. So X, my time for 1 half-life, will be my total amount of time. I have 120 days. And in 120 days, I can do 3. I need to do 3 half-lives. Okay? So every 40 days, I will do a half-life. Okay? So 40 days would be my half-life. That would be my answer. Okay? All right, cool. So getting to our notes, find yourself the nuclear decay notes. Okay? So get yourself the nuclear decay. Remember, we'll come back to ions and atomic spectra. Make sure we're all at nuclear decay. All right, so nuclear decay. We talked about how atoms are made of protons, neutrons, and electrons. Yeah. Talk about how atoms are made of protons, neutrons, and electrons. Normally, atoms want to have about the same number of protons and neutrons, but if the number of neutrons gets too far off the number of protons, we say that that atom is radioactive. Okay? Now, when that atom is radioactive, it's unstable. It wants to decay into something more stable. So we call that radioactive decay. So in radioactive decay, they say it's spontaneous disintegration. What's spontaneous mean? Not random. Out of nowhere. You can think like, yeah, out of nowhere is a good. Unpredictable, maybe. Sometimes that happens quickly. So kind of this unpredictable disintegration of a nucleus. Nucleus makes up an atom into a slightly lighter nucleus. So basically we're going to release some sort of particle, which you see there, along with, they say EM wave. That is an electromagnetic wave. Some sort of electromagnetic radiation. Okay? And then when you do this, you then get yourself to a more stable nucleus, a more stable atom. Okay? So moving on, remember if I'm going a little too fast for you, you can open up the slide deck on your own screen. All right, first kind of decay is called alpha decay. Sometimes called alpha emission. Emission means like the release of something. So alpha decay, alpha emission, is the release of an alpha particle. Okay? Now, you ask, what is an alpha particle? An alpha particle is a helium nucleus. So not an entire helium atom. It's not, you're not releasing electrons with it, just the nucleus of that helium atom. Okay? And this is what like the general formula would look like. You would have some sort of parent atom where X, what does X mean? Say AZX, what would X be? That's your element symbol. X is your element symbol. What would A be, the number in the top left corner? That's maybe a little hard to see with some heads. It's going to be the bigger number. That's your mass number. Okay? And then Z is your atomic number. In other words, we take an element, like let's say if you look here, uranium-238. Okay? If this uranium-238 undergoes alpha decay, uranium-238 is going to release what we call an alpha particle. It's going to release a helium nucleus. Now, a helium nucleus has a mass of 4 and an atomic number of 2. So let me write a little bigger up here. I'm going to write this a little bit bigger so you can maybe see it better. 238, atomic number of 92. And you're going to release a helium nucleus. And then you're going to create a more stable atom. Now the question is, what is the more stable atom that we make? Well, think of this arrow as an equal sign, where the numbers over here, the 238, your mass number, and your atomic number 92, has to be the same on both sides. Okay? So if I have a 4 for a mass number here, I'm releasing a helium nucleus, what would my mass number need to be over here to add up to 238? 234, right? Or in other words, 4 plus what would equal 238? 234, right? Now, what they're trying to show here, when they say A minus 4, because I'm getting rid of a mass of 4, you'd end up subtracting this by 4. Okay? All right, now, if you try to find the atomic number of this more stable atom, it's going to be 2 plus what gives you 92? Be 90, right? Or another way of saying that is 92 minus 2 gives you what? And that'd be 90. Now then, to find the element symbol, you then have to look on the periodic table, and which of these two numbers, the 234 or the 90, do I want to use to find the element? You want to use the 90. Why don't you want to use the 234? There is no, that might actually be true. Let's pretend like there was though. Let's see, you see 234 up there. There's a more specific answer for why you want to use the 234. We talked about, if you remember like second class, talked about like argon and calcium. What did they both share in common? Yeah, every element has, there is only one element on the periodic table with a atomic number, a number of protons, that is 90. There can be multiple elements that have a mass number that's the same. So that's why you want to use the atomic number. So you look up on the periodic table, find 90, and that would go with thorium, TH. Okay? So this would then be the equation for an atom that has done undergone alpha decay. Okay, so you need to know the name of this. You need to know that in alpha decay, you release a helium nucleus. So I was trying to think, how can I get you to remember that? Well, He stands for helium. Alpha stands for alpha decay. So I was thinking the phrase, he is an alpha. Alpha, like, there's the idea of like, like you have like a dog, like the alpha dog, maybe like the lead dog or something. So, anyways, I don't know who he is, but, something to remember, alpha decay, helium nucleus. Okay, second kind of decay I need you to know, beta decay. So in beta decay, also called beta emission, you are going to release what's called a beta particle. All right? Now a beta particle is a high energy electron. Okay? So what happens, you have some radioactive atoms, some really unstable atom, and it's going to release a high energy electron. Okay? And then as a result, we're going to get ourselves to a more stable atom. So in beta decay, like this is the example they have. Iodine 131. Iodine atom with a mass of 131. If it undergoes beta decay, it's going to release this beta particle. A beta particle has a mass of 0, and then for the atomic number, they have a -1. Why would you have 0 and -1 for a beta particle? Any thoughts? You think back to like second class, the parts of the atom. Perfect. It's an electron. It's a high energy electron. Electrons have a mass of essentially 0. And then we said the charge of electron is -1. So this bottom left number, that's the number of protons. You would want to have the opposite of 1 proton if you're an electron. You have a -1 charge. Each proton is a +1 charge. So that's why this is a -1 charge. Now, when I said in the last slide, when you have an equation like this, what's on the left side has to equal what's on the right side. So mass number on the left side has to equal the mass number on the right side. Okay? So if I have a mass of 131 on the left side, I have a mass of 131 on the right side. So that's why the new atom that comes after the decay has a mass of 131. Okay? Now, 53 is our atomic number on the right side. That is why the new atomic number on the right side is 54. Because 54 minus 1 will give you 53. Okay? Then to find the symbol, to know that this is xenon, you look up the atomic number, 54, and you will find that that goes with Xe. Okay? Now then, beta particles, they can damage human skin. They can lead to cancer. You don't want to be exposed to beta particles. Now then, how can you remember what a beta particle is? It's a high energy electron. So here's what I was thinking. I love my new bay. So whenever you release a beta particle, you end up creating beta particle. You end up creating a new element, and then this high energy electron comes out. All right. Yeah.
You don't think that happened in this class?
That people have a new bay that they love?
Like that they created
No, it's not just happening in this classroom casually. No. So, it just doesn't happen, man. They don't trust those kind of radioactive materials. All right, one more kind of radiation. So 3 kinds of high energy particles I know about. Third kind of nuclear decay is called gamma decay or gamma emission. Now, some of you are heard an oh yeah. So if you played, I think it's Fortnite. All right. I don't know, there's a gamma ray gun you'll see in various video games, And the idea why this is a good weapon in some futuristic video games is because a gamma particle is a really, really high energy particle. It's even more deadly than a beta particle. So if you get hit with a gamma ray, that's going to hurt a lot more than you do with a beta, beta particle. All right. Now, there's no equation you have to know for this. I don't give you equations to solve. because when gamma rays get released, they're massless, and there's not like a charge associated with them. So it doesn't actually change the identity of the element. So the element stays the same. Why don't you add that to your slide? I'll add that up here. So element stays the same. Element stays the same. Now, the rest of these bullet points might be a little tough for you to understand right now because we haven't done the flame lab. The flame lab was that lab I was wanting to do with y'all, but I couldn't get enough safety agreements in. But basically what happens, if you were to take a atom and you were to raise the energy of that atom, when it goes from a high energy state back to a low energy state, it can release energy in the form of light. Now, gamma decay wouldn't be like what you would do like in the class in the flame lab. What happens in gamma decay is a similar thing. The atom gets to an even more excited state, but then when it goes back to its more relaxed or its lower state, it will release that high energy gamma particle. Okay, so just kind of, that's a little confusing. It's not super important for like today, especially. It'll make a little more sense when we actually do that lab. Right? Cool. So I need to remind you of the electromagnetic spectrum. So theoretically, you learned this in middle school. The idea of the electromagnetic spectrum is it's the spectrum of light. Now, when we say light, you tend to think of visible light, right? But the same, when you see visible light, that same particle of light will actually be the same thing that makes up radio waves or microwave waves. In other words, radio waves, microwaves, X-rays, visible light, it's all made of the same particle, a photon. It's all part of the same wave, but it's just the difference is whether or not it's a high energy or a low energy wave. So if you shoot a bunch of low energy waves at your food, you have a microwave. If you have even lower energy light waves, you have a radio wave. If you get to super high energy waves, you have the gamma ray. So in other words, you're like, well, what is gamma ray? What is a gamma ray? It is just a super, super high energy particle of light. Okay? Now, with waves, because light is both a particle and a wave, there is a wavelength and a frequency. You don't have to worry about that for right now. I more just want you to focus on low energy, high energy. Just kind of, another chance for you to see this spectrum. I'm not necessarily going to test you on it exactly. I more just want you to think about like where these gamma rays come from. Okay. All right, so now getting into more of the questions you would see on the formative, some more practical stuff. All right, so I'm going to write this a little bigger. I know it's a little small. So we have polonium. Let me go over a little further to the left. We got polonium 260. And they're saying polonium 216 goes to astatine 216 plus some kind of radiation. So the question they're asking you is, what is the radiation that's being released? What do we think? What would I fill in that blank there? Yeah, go for it. Yeah, beta. Good. Now, how you represent beta, you can either do like a B with an elongated tail, or you could show it as an E, because remember, it's a high energy electron. Now, if you're like, how did he know it was a beta particle? Well, you have to compare the mass and the atomic numbers. Remember, left side and right side have to equal each other. So 85 plus what will give you 84? Plus negative 1, right? 85 plus negative 1 will get you 84. 216 plus what gives you 216? 0, okay? So that's how you know it's a beta particle. It's really like it's pretty simple. Like it's the idea is very straightforward. You just got to remember what it's called, like what you would call that. All right, now let's look at the second one here. Second one, they're telling us we have potassium 42. And then now they're kind of flipping on us. They're telling we need to find the isotope that comes from potassium 42, given that it's undergone beta decay. So what would be the isotope that we get from beta decay? If we do beta decay, what would we get out of that? Remember, left side and right side got to equal each other.
42 and 20.
So let's get some hand. Let's get a hand for this. Otherwise, just a little too much shouting. Yeah, go ahead.
It's going to be 42, 20.
Yeah, good. 42 and 20. Perfect. Left side, right side got to equal each other. 42 and then 20. Now, to find the symbol that goes here, don't use the 42 because notice how two things have a mass number of 42. Use the atomic number. Go to the periodic table, find the element that has 20, and what would it be? You say elements. Calcium. Ca. Okay. Not bad, right? So that'd be an example of beta decay. All right, let's do this one. I'm going to write this one a little bit bigger over here. So yeah, that's not a 9. Got Pu 239. And we don't know the atomic number, so that's an unknown. They ask us for the element that comes from this. And they're telling us it's undergoing what kind of decay? Alpha decay, right? He is an alpha, it's helium nucleus. All right, so then we have three things, well, two things to answer. The first is, what is the atomic number that we put there for the Pu? And the second is, on the right side of the arrow, what is the isotope? What is the stable element that comes after we do alpha decay? Who could give me the atomic number? What would that be? So here's what you do. Find Pu on the periodic table. So it's a little hard to find.
It's down. There.
Yeah, oh yeah. All right, here we go. 94. Okay. So you found Pu and it is 94. All right. Now then, what is the stable isotope that we get?
Uranium.
Say uranium? Yeah. Uranium. Now, what are the numbers that would go here, though? What would be those two numbers?
92.
92, good. And then what about the mass number?
238.
Not 238. 235. So remember, left side and right side numbers have to equal up. So you'd have to ask yourself, 4 plus what number would equal 239? And that would be 235. And for the atomic number, 2 plus what number equals 94? That would be 92.
The element that you put in the middle is just like 92, that atomic number.
Yes, yeah. This would, yeah. How you know this is U is you would go to 92, and you see that 92 goes with U.
So you find the atomic number first by like doing what adds up to 94.
Yeah.
You go on the chart and find it and put it in the middle.
You got it.
Yeah,
Okay. It's really, like, half-lives is definitely harder than this. This is definitely easier than half-lives, but you just kind of got to see the pattern with this. All right, got one more in this slide. We got uranium 235. Okay. Atomic number of 92. This is going to go to, now here they're flipping the order. Notice how I've always been writing the isotope and then the radiation. They can go either way. Here they're asking for the radiation, and then they write the isotope, the stable isotope that comes from it. In this case, it's thorium 231. Okay, so then what isotope would I put there? Yeah, good. Helium. And what are the mass and atomic numbers?
4-2.
4-2. And then you need to understand, you need to be able to then say it's alpha decay. Okay? So you may be able to solve these equations, but remember, he is an alpha, so you know it's alpha decay. Okay? All right, we got questions on that? Was it? Oh, do I have more practice problems for you? Oh, I got, I want to do this slide. I'm going to skip over this one. This is the same thing as this. I'll let you fill that in if you need some extra practice. Let me just run through this real quick. This is just going over like the comparative strengths of these three kinds of radiation. And then how you would stop these three kinds of radiation. So, the weakest kind of radiation is alpha decay. Okay? So alpha particles are the weakest.
What's the difference between radiation and isotope?
The radiation would be like the beta particle, the alpha particle, the gamma. That's the particle of light that's being released. The isotope is the actual, like, it would be an actual atom. Like you could find it on the chart.
Good question.
All right. If I want to stop a ray of alpha particles, I can just use a piece of paper. Now, if beta particles are in the middle, if I want to stop beta particles, I would need like a decently thick piece of aluminum. Now then, if I'm getting hit with a bunch of gamma rays and I want to stop those, I would need some concrete. That's because gamma rays are the strongest. Now, question for you. Why would it make sense that alpha particles would be the weakest? That I could stop it with like the smallest thing? Think about the structure of an alpha particle compared to the structure of a beta particle and the structure of a gamma ray. So raise your hand for it. You got it? Yeah. Yeah, it's the highest energy. Okay, good. Yeah, so the highest energy, so you need concrete to stop it. Going back to the alpha particle, what is unique about the alpha particle compared to the beta particle and the gamma particle? The alpha, it has mass. The alpha particle, it had a mass of 4, right? The beta particle had a mass of 0, effectively 0. Gamma particle didn't have any mass. So basically the alpha particle is really, really big and bulky compared to these other radiations. That's why you can just stop it with a simple piece of paper. But the beta particle, it's super tiny, and then a gamma ray, it's just like light, essentially high energy light. So it's able to get through. You need a much more substantive, like a bigger thing to be able to stop those kinds of particles. All right, I'll let you start working on the formative. Again, this slide here, I'll leave it filled in there for you. I'm not going to run through them again. Let you fill that in, and then, but it's a similar type of problem. All right, I'll be going around if you have questions.